Okay. Today I present a second approach to develop a quadrature rule for the computation of this integral. Take a review about trapezoid and Simpson's rules. This is a trapezoid rule. Yeah, this part, this number is the area of a trapezoid. So we call this formula trapezoid rule. The error term is this. And for Simpson, the error term is this. Because the error involves derivative, second derivative. So trapezoid rule is exact for all polynomials of degree not greater than 2, right? Polynomial of degree not greater than 2 takes second derivative. Second derivative is 0. So therefore, if f is a polynomial of degree not greater than 2, quadrature polynomial, then trapezoid rule is exact. Yeah, the area of trapezoid is exactly equal to the integral. For Simpson's rule, because Simpson's rule, error term involves derivative of order 4. So Simpson's rule is exact for all polynomials of degree not greater than 4, right? Am I right? Let me see. X4 take derivative is 4x3. Take derivative again. It is x2. Take derivative again. X derivative again. 1. Oh no. For Simpson's rule is exact for polynomials of degree not greater than 3, and trapezoid rule is exact for polynomials of degree not greater than 1. Not greater than 1. Okay. Yeah. Because of this observation, a quadrature rule is exact for some polynomials. This observation motivates a second new approach for deciding quadrature formulas for an integral. Okay, this is what I want to tell today. Okay, a method of undetermined coefficients. This is a new method. Okay. Topic 1. Let me make the integral slightly more general. Consider this integral a b function f then times w some function. We call w this function a weight function. I want to compute this integral. Then the formula, I want the formula has the following form. Okay. From the interval a, b, let me pick some distinct loops. X0, x1, xn. Okay, pick some loops from the interval a, b. Then I want a formula like this. A constant A0 times function value at the log x0, then plus A1 function value at x1, and so on. An function value at xn. I want a rule like this. Okay. Then because A0, A1, An, this will be determined. How to determine the coefficients? I want this formula, this approximation, the approximation except for polynomials of degree. How many freedoms that we have? N plus 1 freedoms, right? A0, A1, An. So I want this approximation except for polynomials of degree log greater than n. Okay. Okay. Now because a polynomial is a linear combination of these n plus 1 special polynomials. Right? This is a basis polynomials. Any polynomial of degree not greater than n is a linear combination of these n plus 1 special polynomials. Now, let me plug in these polynomials in this formula. Okay. Plugging 1 in F, then we get integral 1 except, okay, so equal. Plugging function is 1, so A0, A1, An. Now, plug in the second special, the basis polynomial x in the F. Except, okay, F now is x, so we have A0, we don't know what A0 is, will be determined, times x0, I know x0 given, okay, then plus A1, x1, An, xn. Plug in x squared in F, then I get A0, x0 squared, A1, x1 squared, and so on. Okay, now plug in the remaining basis polynomials. Then we have a system of n plus 1 linear equations about the coefficients. Plug in An. A0, x0 n, A1, x1 n, and so on. This is a system of n plus 1 linear equations in the unknowns. The unknowns are the coefficients A0, A1, and An. Then solve this linear system. We get the coefficients. Then we get a quadrature rule. This rule is except for all the polynomials of degree log greater than n. Okay. As an illustration, let me show you 2 examples. Then take a look at the following 2 examples. Example 1. I want a formula, okay, for this integral. 0 to 1, f the wave function is equal to 1. Okay, I want a formula. This is an approximation, not equation. the nodes, I pick the nodes between 0 and 1. X0 is 0. And A1 is the midpoint, 1/2. And A2, the right endpoint of the interval 0 to 1. So 1, 1. Yeah. I want a formula of this form. Okay. I want to make the approximation except for polynomials of degree log greater than 2. Okay, log greater than 2. Okay, then how to determine the coefficients? Okay, substitute the basis polynomials 1 x squared. Then plug in 1 in f, integral from 0 to 1 on 1. It is equal to 1. Then exact. Okay, approximation is exact. Okay, then f is 1. So A0, A1, A2. First equation. I plug in x in f. This integral is computable. It is equal to 1/2. Now function is x. So the value of x as 0 is 0. So the first term is 0. Now the second term, 1/2 A1. Third term, f is x. So A2. Second equation. Plug in x squared in f. This integral is 1/3. 1/3. Okay, now f is x squared. First term, again, 0. Second term, A1 times function value. Function is x squared, so square. And then A2 times 1 squared. Okay, so 3 equations, 3 unknowns. Solve it. The solution is A0 is 1/6. A1 is 2/3. A2 is 1/6. So therefore, we have a formula to compute this integral. 1/6 F0, 2/3 F 1/2, and 1/6. Yeah, we have a formula. So this new approach doesn't use interpolation polynomial to approximate function f. Okay, this is a new approach. This is example 1. Now, second example. Take a look. Second example. Example 2. I want to compute this integral. Negative pi to pi. Function times. Now, the weight function w is cosine dx. Okay, now I design a quadrature rule for this integral of the following form. Now the integration interval is negative pi to pi. Now let me pick row. The first row, 3/4 times pi. Okay, this is an x0. Now function value at this row. Coefficient is a0. Then A1. The second note I pick -1/4 pi. And A2 1/4 pi plus A3 3/4 pi. I want a formula like this. Okay. Now, how to determine the coefficients? 4 coefficients, 4 unknowns. So we can expect this approximation is exact for polynomials of degree not greater than 3. Right? We want the approximation exact for polynomials of degree not greater than 3. Not greater than 3. Okay. Now, polynomial of degree not greater than 3 is a linear combination of 1, x, x squared, and x3. Right? Basis polynomials. Okay. Now, let me plug in 1. Okay. Plug in 1 in F. Our function is 1, so cosine x dx. Now, approximation is exact. Function is 1, so the right side is this sum. Okay, this sum. Okay, this integral computable. Okay, computable. It is 0. First equation. Okay, first equation. Now second equation. Plug in x in the function f. Then we get pi x times cosine equal. Okay, now function is x, so -3/4 pi times A0 minus 1/4 pi times A1 plus 1/4 pi A2 plus 3/4 pi A3. Second equation. This integral again is 0. Actually, x times cosine is a half function. Half function, and the integration interval is symmetric about 0, so integral is 0. Okay. Plug in x squared in F. X squared cosine. Then we have A0 times -3/4 pi squared plus A1 -1/4 pi squared plus A2 squared. The equation. This integral is -4 pi. Finally, plug in x to the third in F. This integral, its value is 0. Why it is 0? Because the integrand x to the third times cosine, an half function, so integral is 0. And then the right side is A0. The A1, A2, A4. A system of 4 equations, linear equations. So solve this linear system. We have the coefficients. It turns out that the coefficient is, the result is A0 is -4/pi. A1 is 4 over pi. A2, 4 over pi. A3, negative 4 over pi. The answer. So to compute this integral, we have this formula with these coefficients. Then the approximation is exact for polynomials of degree log greater than 3. Log greater than 3. Yeah. This is the so-called method of undetermined coefficients to design a quadrature rule. Okay. Now, topic 1. Now, second topic. Let's turn to section 3. Gaussian quadrature, popular method. Okay, popular method. Okay. In section 2, this quadrature rule, we first take the logs. So in this formula, the logs are fixed. How about we also let the logs free? Then we have how many freedoms if we let all the logs are free to choose? How many freedoms that we have about this approximation? Freedoms, how many? Freedoms. We have freedoms to choose the coefficients. So this is n plus 1 freedom. Now we also have freedoms to choose the logs. How many freedoms? N plus 1. So in total, we have 2n plus 2 freedoms to decide this quadrature formula. Now, 2n plus 2 freedoms, we can expand this approximation except for polynomials. Okay, then we can expect the approximation in this formula except for polynomials of degree not greater than 2n plus 1. You agree? You agree? Okay. And the resulting method, the resulting formula is called Gaussian quadrature rule. Gaussian quadrature rule. Okay. Now, this is a topic 2, Gaussian quadrature rule. Topic 2. Topic number 2. Okay. We want a formula of the following form. A weight function. Okay. Weight function. In Gaussian quadrature rule, we assume the weight function greater than 0, positive everywhere on this interval AB. Okay. Because only when W greater than 0, we can develop nice theoretical results. When W is a general function, not many nice theoretical results. Okay, so here I assume W greater than 0. Now, I want a formula of this form: A0 F X0 plus A1 f x1. Okay. Now this time, all the quantities, the coefficients and the logs are free. Okay, free to choose. Okay, of course, where I assume x0, x1, the logs, all in this interval and distinct. Okay, and distinct. Okay. Okay, now we have 2n plus 2 freedoms. So we expect this approximation except for polynomials of degree 2n plus 1. Okay. Okay. The basis polynomials are 1, x, x2 until x 2n plus 1. Okay. So in total, there are 2n plus 2 basis polynomials. Now I plug in these polynomials in the F in this approximation, then I get a system of 2n plus 2 equations. Now this time, the equations no longer linear. Okay. Plugin 1. W x A0 A1 AN. Okay. Plug in x in F, second equation. This is an x times function W. And then now F is x, so the value is x0. x0 times A0. x0, A0, they are unknowns. So at least the first term is not linear. And then the second term. All right, now plug in x squared. X squared. The first term here is an x0 squared. x0 unknown. And so on. Plug in the last function times W. x0 to n plus 1. A0. x1 to n plus 1. A1. And xn to n plus 1. AN. Yeah, so this is a system of 2n plus 2 non-linear equations. Usually, same number of equations with the same number of unknowns can determine the unknowns, can determine all unknowns. Then solve this system. We can get the quantities A and the quantities X. Then we have Gaussian quadrature. But solve this system not easy because they are non-linear. We need to develop methods to determine the coefficients and the logs in Gaussian quadrature. Not through this way. This is too difficult. Okay. Now, the approach below is nicer. Okay, not through the solution of this system to attain the coefficients and the logs, but through other approach. Okay. First, let me present one lemma. Okay, one lemma. Okay. This is a lemma. I present the lemma without its proof. For the proof, if you are interested, take a look at the book. Okay. Let the weight function positive greater than 0 on the interval AB. Otherwise, we don't have this lemma. And also continuous. Okay. So continuous greater than 0 and in this space continuous. Second, let Q be a polynomial of degree n plus 1. Okay, n plus 1. Then is W orthogonal. What it means, W orthogonal? I will tell you. A Q, this polynomial degree is n plus 1, and is W orthogonal to all the polynomials of degree log greater than n. Yeah, the notation is this. Okay. Yeah, this notation. The set of all polynomials of degree not greater than n. Okay. Yeah, Q is orthogonal to all the polynomials of degree not greater than n. Orthogonal, W orthogonal, what it means? The meaning is in the following sense. In the sense that for any polynomial from this set, we have integral a to b q times p w orthogonal times w. This integral is 0. Okay. When this integral is 0, we say that a q is polynomial is orthogonal, w orthogonal to p. Yeah. Right. This is what w orthogonal means. Means is integral is 0. Okay, it's 0. Okay. Now conclusion. Okay. Then conclusion. Then Q this degree is n plus 1. A polynomial of degree n plus 1. How many roots the polynomial has? N plus 1 roots. Okay. Then the n plus 1 roots of this polynomial are all real numbers. The root of a polynomial may not necessary to be a real number. Say for example, x squared plus 1. The root of this polynomial is a complex numbers, okay, but not for q. Okay, the q is root all are real numbers, and also distinct, different, and all lie in the interior of the interval AB. Interior. That means that all the roots are in this open interval. Yeah, open interval. Greater than A, less than B. Interior. This lemma, I don't present the proof. Okay. If you are interested, take a look at the book. Okay. Okay. Now, in Gaussian quadrature, the roots actually are the n+1 root of this polynomial. So you don't need to solve this system. This is a non-linear system. Impossible by hand. Solve it by computer. Impossible by hand. But it turns out that we will see. It turns out that all the roots in Gaussian quadrature are the roots of this orthogonal polynomial. Now, next, based on this lemma, we have the following theorem. The following theorem. Okay. Theorem. This theorem is on the coefficients and the roots of Gaussian quadrature. Okay. On Gaussian quadrature. Gaussian quadrature is very popular. Okay, very popular because this quadrature rule is except for polynomials of degree 2n+2. Okay, very accurate. And then W greater than 0, and in this space. All right, let Q, the Q in the lemma, let Q be a polynomial of degree n+1. This Q is in the lemma. That is W orthogonal to this set. This set is the set of all the polynomials of degree log greater than n. Okay. If x0, x1, x2, xn okay, choose the root of this Q as the root are the root of Q. And okay, now we have the roots for Gaussian quadrature. Now, how about the coefficients A? Okay, and choose A, AI in this way. Take integral from A to B, W, the wave function, times L, the cardinal functions in Lagrange interpolation. Where Li cardinal function, okay, x minus x0 times x minus xi minus 1, but don't times x minus xi. Skip x minus xi. X minus xn, then over xi minus x0, xi minus xi minus 1, xi minus xi. Yeah. Okay. Don't use if. Don't use if. Okay. Let me use choose the logs as the roots of Q and choose A in this way. Then this formula, let me give a name to this formula. Say, let me call it 1. Okay, 1. Okay, this formula 1. Then 1 is exact for all function f in this set. This set 2n plus 1. That means that for formula 1 is except for all the polynomials of degree not greater than 2n plus 1. Okay. So by this theorem, we don't need to solve this system. This system almost impossible to solve theoretically. Okay, theoretically, yeah. How to prove this theorem? The proof, not difficult. The proof, okay, not difficult. Okay, now let me arbitrarily take a polynomial from this set. Let f from this set. Okay, now f is a polynomial. Okay, then divide this polynomial by this q, okay, by q. Okay. Okay. We have f is equal to q, then the quotient times quotient, also a polynomial. P is a polynomial. Then the remainder R. Okay, R. Remainder. Okay, yeah, this guy degree n plus 1. Remainder, the degree cannot be greater than or equal to n plus 1. So the degree at most n, degree n. And because f is 2n plus 1, the degree. So p, the degree at most n, at most n. Yes, at most n. Okay, now next, write polynomial R in Lagrange polynomial. Okay, R, write it in Lagrange polynomial. The value of R at the log x0 times cardinal function. Yeah, cardinal function degree is n. Then plus Rx1 cardinal function and so on. Rxn cardinal function. Why we have this equation? By the uniqueness of interpolation polynomial. Yeah, this is a polynomial of degree at most and most n, right? Yeah. About this equation, the right side, the polynomials are degree n, and the right side, the value at x0, x1, xn values are arrow x0, arrow x1, and arrow xn. So the right side is a polynomial of degree log greater than n and interpolate arrow at these logs. The left side, degree n, and also interpolate the function itself at the n+1 logs. So these two left, the polynomial on the left side and the polynomial on the right side, they are equal. So we have this equation. Now we have arrow. Now take integral. Take integral on this equation on next page. Take integral. AB f x w. Take integral with w. That is equal to AB. Plug in this equation. Yeah, plug in this equation. QP arrow. QP arrow. W. Dx. So we have AB QP W dx plus AB arrow times W dx. But P degree is n. Q degree n+1. But we assume that Q is orthogonal to all the polynomials of degree log greater than n. So actually, this term is 0. Yeah, here. The assumption, okay? Yeah. Q is W orthogonal to this set. That means that this integral is 0. So we have AB arrow W. Okay. Now plug in this equation. Plug in this equation. Okay. So this is a AB summation I from 0 to n arrow xi li x times W. Okay. Okay. Now move switch integral and sum. And also move out the constant. Yeah. Yeah. Also move on arrow xi integral li x w dx. Right. But this number, this is a number. But this number, by definition here, is this number. So it is AI. So yeah, this is a AI. So we get summation I 0 n AI times R xi. However, from this equation, f xi is equal to q xi p xi plus r xi. But recall that the logs are the roots of q. So qxi is 0 because xi is a root of q. So this is equal to r xi. So therefore, this is a summation I from 0 to n ai f xi. So for any polynomial from this set 2n plus 1, we have equation. In other words, this approximation for any f polynomial of degree log greater than 2n plus 1, we have equation here. So therefore, if we choose the logs as the root of this orthogonal polynomial and choose the coefficients in this way, we obtain Gaussian quadrature. Now the next question is, I don't have time. Next class, I tell you how to find Q, how to find orthogonal polynomials Q. After we get Q, we can compute its root. After we get the root of Q, then we have Gaussian quadrature.